Welcome everyone to section number 6. This is directional derivatives and this thing called the gradient vector. And so in this video we're just going to give some definitions. We're going to see what a pain the directional derivative actually is. So we're going to define this thing along with defining the gradient vector. And then we're going to see, right, the directional derivative will be a pain to calculate, but actually we can use this thing called the gradient vector to help calculate out the directional derivative. So we'll do that as well. So, all right, let me give you the definition here. We have the directional derivative of our function f at a specified point, x naught, y naught, in the direction of, right, we have to specify the directional derivative. Well, what direction do you want me to go, right? So in some direction, right? So, and this needs to be a unit vector. So and so this is maybe a comma b, right? Okay, here's the notation. So we're doing in the direction of u of our function, right? And we want the derivative. This is going to be equal to the limit as some h goes to 0. And this is going to look a lot like our partial derivatives, right? But we're actually going to be splitting up this h. Remember, for when we just did a partial derivative with respect to x, the entire h was in, that first component. So let me go ahead and start writing this out. So f of x naught plus, I'm going to split up, some of the h will go here. In fact, a of it will go here. Y naught plus, and then h, some of it will go here. How much? The b amount, right? Minus our function at x naught, y naught, all divided by h. So this kind of looks a lot like our partial derivatives, but we're just divvying up the h. We're not saying, hey, all of it go here or all of it go here, but we're going to put some in each. Okay, let's go ahead and calculate this out once. Calculate the directional derivative at the point 1, 1. So that's our x naught, y naught. Let me go ahead and maybe label this. Here's our x naught, y naught in the direction of 1, 2. And already I see we have a bit of a hiccup here, right? Because this is not a unit vector. If I go ahead and calculate out the length of this thing, right, the length of 1, 2, well, this is equal to the square root of 1 squared plus 2 squared, right? So this is equal to the square root of 5. So this is too long of a vector, right? So I would like to substitute in, right, the same direction. However, I'd like it to be a unit vector. So I'm going to go ahead and say my unit vector that's in the same direction as this one, should be 1 over root 5, comma 2 over root 5. So we got to go back, and we're using our skills back a long time ago, chapter 12, when we brought up all this stuff about unit vectors and how to find those, right? So this is just dividing by that length. Divide each component by the length, and this will now be a unit vector. So if you double check and find the length of this, it'll be 1. Okay, so now let's go ahead and write down our definition. So we want the derivative in the direction of u of our surface f. So here's our f surface right here, x squared plus y squared, at 1, 1. So this is going to be the limit as h goes to 0. And okay, so first thing, we need to go ahead and calculate this. So we have the function at 1, comma ha. All right, so this is a lot here. So our function, right, our function is x squared plus y squared. So we're going to go ahead and take the x component and we're going to square it. So our x component here, well, that's x sub 0, 1, plus h, right? So that's just a variable. This is going to be going to 0, times a. Remember, a is that x component of our unit vector here. So that's going to be 1 over root 5. And the function says square that. Plus the y component squared. So the y component, y sub 0, that's 1, plus h times b. b, again, is the y component of our unit vector. So that's going to be 2 over root 5. And again, this needs to be y squared. So we took our x component, we squared it. We took our y component, we squared it, right? Minus the function evaluated at x naught, y naught. So, okay, minus the function evaluated at x naught, y naught. So that's going to be 1, 1. So if I plugged 1 in for both of these things, well, that would be 1 squared plus 1 squared. Well, that's going to be 1 plus 1. That's going to be 2. So we're going to go ahead and subtract away 2 from that. And now all of this divided by h. All right, now we have a few lines of simplification, right? So the limit is h is going to 0. And let's expand out the squaring right here. Right, so in fact, let me go ahead and I'm going to rewrite this with the h and the 1 on top, right? We can go ahead and multiply these fractions, and I can just go ahead and put the h on top. Likewise, over here, this is just going to become 2h. To make life a little bit nicer for us. Okay, so if I expand this, right, remember, this is technically foiling. We need the first, the inners, the outers, and the lasts. And so I'm going to go ahead and get, long line here. So let's see, 1 plus 2h over root 5 plus h squared over 5. So again, that's foiling this out with the inners, the outers, everything. Plus, all right, 1 squared plus 4h over root 5 plus 4h squared over 5, all minus 2. And actually you can see very nicely the 1, and the negative 2, these all perfectly cancel out. And this is all being divided by h. And now you see what's happened here is that, well, everything without the h's has gone away, and now all of these terms actually have an h in them. So let's go ahead and factor that out. So I'm going to have the limit as h goes to 0, and I'm going to factor out an h from everything in the top here. And so from the first one, I'll have 2 over root 5. From the second one, if I factor out an h, I'm going to have an h over 5 left. Here I'm going to have, let's see, a 4 over root 5. And then if I factor an h out of this one, I'm going to have 4h over 5 left. So I factored out an h, and now we can see that this factored out h over here will nicely cancel with the h in the denominator. Now that there's not an h in the denominator, right, I've been itching to plug in 0 everywhere I see an h. However, with the h in the denominator, I'd be dividing by 0, so I couldn't do that. But now I don't have any issues plugging in 0 everywhere I see an h. So when I do that, let's see, I'm going to have 2 over root 5 plus 0, well, 0 fifths, I guess, plus 4 over root 5 plus 0 fifths. So that's going to be 6 over root 5. So this is saying that the function is increasing. If I was to look in this direction, the 1, 2, and I was hanging out here on this surface, that it'd be increasing, and it'd be increasing in the amount of, well, 6 over root 5, whatever that number is. And as I told you guys, and now I hope that you probably agree with me, that calculating these directional derivatives are a pain. So we'd like to be able to do this faster, right? We want a faster way to be able to calculate out these directional derivatives. And so in order to do that, I've already told you that, well, we're going to use the gradient vector. So let me go ahead and define this for you. If a function of two variables x and y, then the gradient of f is a vector function, and it looks like this. So it's almost like a triangle, but it's upside down. So that's the gradient of f. And this is defined by, well, again, it's a vector function. So in the first spot, we're going to have the derivative of f with respect to x. And in the second spot, we're going to have the derivative of f with respect to y. That seems kind of like a natural vector, right? You can also write this as, the partial of f with respect to x in the ith component. Right, this is the vector I, plus the partial of f with respect to y in the jth component. Right, so this is using kind of our standard base vectors here. Alternatively, right, this can be denoted as grad f. It's again short for the gradient. So if you're maybe doing this on a keyboard or something like this, where you don't have this upside down triangle, you can just call it grad f. It can also be pronounced as del f. I don't exactly know why del f, but okay. That can be a fun Wikipedia search later for me. Alright, so this is a perfectly fine vector. The question is, well, how does this help us calculate out this directional derivative? And so this is one of the important things about this gradient vector. So again, if we have u is some unit vector, and we want to calculate out the directional derivative in that direction of u of some surface f that has x's and y's, well then the claim is that this is the gradient vector dot u. The gradient vector dot u, and of course we need to evaluate at the specific point. So maybe let me be specific here. So evaluated at x naught, y naught dot u, our unit vector. So this is going to be way, way, way easier. In fact, you can see we're going to do the same problem again here, but I've given us way less room. Let's go ahead. Well, first of all, we already know our u in this case is going to be equal to 1 over root 5, comma 2 over root 5. So again, this is in the same direction as 1, 2, but it's a unit vector. Now let's go ahead and calculate out our gradient. So the gradient of f, well, we need, in the first component, we need the partial derivative with respect to x. So that's going to be 2x. In the second component, we need the partial derivative with respect to y. So that's going to be 2y. And so we need the gradient evaluated at our point of interest. In this case, our point of interest is 1, 1. So the gradient evaluated at 1, 1. Well, everywhere I see an x, I plug in 1. Everywhere I see a y, I plug in 1. So that's going to be 2, comma 2. All right. So according to this theorem up here, we take the dot product. So we want to dot 2, 2 with 1 over root 5, comma 2 over root 5. So when I do that, well, let's see, we have 2 over root 5 plus 4 over root 5, and that is 6 over root 5, which was the same answer that we got before. So we can see that this is way, way, way faster than all this up here, right? With this limit as h goes to 0, and it's complicated. It's easy to plug in the wrong things in the wrong places, right? This is so much easier and so much faster. So that's why we love the gradient vector. And now it actually turns out that the gradient vector is good for more than just, calculating out directional derivatives. In addition, the gradient vector, right, will answer an important question, which is, which direction should I go to maximize the directional derivative? That is, having my function increase the most. So for instance, imagine that I'm sitting here on this mountain, here at this specific point, this x naught, y naught maybe. So I'm at this point, and I want to know what direction should I head in order to what's the steepest direction, or what's the, maybe we could even ask an expanded question, what's the least steep direction? What takes me straight down or what takes me straight up? So in this case, I want to know what is the direction that kind of increases the fastest. So, based on this picture, I would guess it would be something like this. And so that's something else that this gradient vector helps us with. So let me give you the theorem here that formalizes this a little bit more. Suppose f is a nice differentiable function, all right, the maximum value of the directional derivative, right? Which way maximizes the directional derivative? Well, the maximum value is the magnitude of the gradient evaluated at that point, x naught, y naught. So if you want to know, okay, what is the maximum of the directional derivative, that's how you find it. And it occurs when u has the same direction as the gradient vector itself. And again, going to be evaluated at that point, x naught, y naught. And this is a theorem, right? So with theorems, there are proofs. This one's actually relatively short, so I'm going to give it to you here. So suppose we have, let me back up here a second, blah, 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 blah. All right, so I would like to show, first of all, that the directional derivative is maximized by the magnitude of the gradient. Well, remember the directional derivative is given by a dot product, right, between the gradient and this directional vector u. Well, let's go ahead, and we're interested in what is that maximum. So, well, the dot product can be given by the magnitude of the gradient times the magnitude of u times the cosine of the angle between them. Right? So that's one of the properties of the dot product back from the day. Well, remember, this is a unit vector, right? Because this is a unit vector, we know its magnitude is going to be 1. So therefore, if that's 1, well, we can simplify this down. And remember cosine. Cosine is nicely bounded, right, between 1 and negative 1. So the most that this quantity can ever be is, well, if cosine's 1. And if cosine is 1, then this is just going to be the magnitude of the gradient. So that's why this first bit is true. Well, and the question is, well, when is that maximum achieved, right? We want, when is that cosine equal to 1? What will maximize? What direction should we choose where this cosine value is maximized? Well, that happens, right? Cosine of theta is equal to 1 when theta equals 0, right? So what angle should u be away from this gradient? Well, it should be angle 0. It should be in the same direction, right? Theta equaling 0 would be in the same direction as the gradient vector. All right, so notice that this proof actually helps us do more, right? So we can actually determine which direction minimizes the directional derivative, right? Then you would want to maybe make this as small as possible. We'll get into that more in class. So let's go ahead and apply this theorem really quick to finish up this video. So same function here, but now we want to find the maximum rate of change and the direction in which it occurs. Right? All right, so finding the maximum rate of change, well, that's going to be the magnitude of the gradient evaluated at that point. So again, the gradient here, we're going to take the derivative, the x derivative, put that in the first component. The y derivative, put that in the second component. And we want the gradient actually evaluated at 1, 1, right? So this is evaluated at the specific point. In this case, our point is 1, 1. So that's going to be 2, 2. Okay, well, if I want to figure out what is the maximum rate of change, well, let's go ahead and take the magnitude of this. So if I take the magnitude of 2, 2, that's going to be equal to the square root of 2 squared, that's 4, plus 2 squared, that's 4, so this is going to be the square root of 8. And if you really like putting these into the reduced radical form, then this would be 2 root 2. So that is the maximum rate of change. So let me go ahead and say max rate of change. All right. And the second question is, and the direction in which it occurs. Well, it's going to occur when u, our directional vector, is in the same direction as the gradient vector. So which direction does it occur? Well, it's going to occurs in direction of 2, 2. Now we have to be a little bit careful here. Sometimes, especially on our web work and maybe on quizzes and exams and stuff like this, if it asks for a directional vector, you may want to put this as a unit vector, right? So I would want to divide by its length here to make this a nice unit vector. This is not a unit vector, right? It has a length of 2 root 2. So maybe a better answer would be if I go ahead and I divide each component by 2 root 2. So let's see, 2 divided by 2 root 2, that's going to be 1 over root 2, right? Because the 2's will cancel. And then here I have 1 over root 2, because again, the 2's will cancel. So this would be an even better answer. So, okay, here is the maximum rate of change, and here's the direction it occurs in. So let me go ahead and note this direction. Occurs in the direction. There we go. I already said it. Okay, and last thing before we go, let's go ahead and verify our answer. So go ahead, we can go to this site right here. All right, and I have it already pulled up here. So here's my nice function. Maybe I can scroll down a little bit here. You can barely see it. X squared plus y squared. Like maybe if I close this. X squared plus y squared. You can see I've plotted the point 1, 1. And when I do that, 1, 1, it's at a height of 2, so I wanted it to show up on the surface, so I gave it the z value as well, so it would nicely appear on the surface there. And now I'd like to go ahead and look at the gradient vector. So I went ahead and I pulled up this right here. We can see it's at -2, -2, which is nice and everything. This is just how it came. I want it at 1, 1. 1, 1, right? That's where I want to figure out the gradient vector. What is the direction of the maximum rate of change? So, okay, there's my point. And if I go ahead and ask for it to plot that gradient vector, so show gradient at point. There we go. And I thought it was going to appear down here as well. Maybe not. Let me go ahead and move these things. There it goes. I don't know why it wanted me to click on that. So you can see that the gradient at this point is going away from this origin. So we can see maybe if you go away from this origin, that, yeah, this seems to maximize our rate of change. That if I was to take a step in this direction, that I would go, this would be very steep up this kind of, parabola looking thing. It would be very steep, so this actually will maximize the rate of change. So this is saying that we should head away from that origin, which kind of makes sense, right? So 2, 2 is perfectly away from the origin. So that actually is the vector 2, 2 there. And that maximizes the rate of change. All right, that's it for this kind of intro video. We're going to be doing a lot more examples and talking about a few more details, maybe minimizing directional derivatives, and maybe we don't want the function to change at all. What kind of direction would we head in then? That's all to come in class. I'll see you guys then.